All right, here we go. So if you have the minimum polynomial x minus 1 squared or x squared plus 1, both of these indicate that we can't diagonalize the corresponding endomorphism, right? This one, because it's not the right form. I mean, you've got the characteristic value is 1, but it's not appearing in as a linear factor in the minimal polynomial, so that means it's not diagonal, according to the theorem we just went through. This, on the other hand, doesn't even have eigenvalues if the field is real. Now, in the complexes, well, then everything's a little bit simpler, right? But we'd like to understand more about this. Like, what went wrong here? What's the next best thing we can do? If we can't diagonalize it, what can we do? And so that's what the triangular form theorem tells us. It says, well, if you can't diagonalize it, if you got all the eigenvalues, if all the characteristic values are actually in your field, even if you can't diagonalize it, you can at least put it in triangular form. So here it is. Let T be an endomorphism over a finite dimensional vector space, minimal polynomial of this form. In other words, the characteristic values are in the field, possibly repeated though. And yeah, and we're writing them distinct, so alpha 1 is not equal to alpha 2 and so forth. Then there exists a basis for V, for which the basis for T, the matrix for T rather, is in block diagonal form, where the blocks are formed A1 through AS, and each AI is a DI by DI matrix for some DI greater than EI, EI being the power that appeared in the minimal polynomial, and DI being the size of the block. And so it looks like this. Alpha, the ith block has got i's down the diagonal, like that. So basically, if you can envision this, on the diagonal, it's just the characteristic values, like, written like that, with repeats, and then for each block. All right, here's the proof. It's going to take us a little bit, but I'll try to be brief. My proofs here, by the way, mostly I'm just working through what Curtis has written, just trying to expand on it a little bit. If you read Curtis and you understand it, then you probably don't even need to watch this, really. Anyway, so here we go. T and endomorphism, M of x looks like this, as in the theorem. Define Vi to be the kernel of T minus alpha I to the I, all right? And let Di be the dimension of said kernel. And let's let beta I serve as a basis for Vi. We know we can do this, all right? By the primary decomposition theorem, we have that V is the direct sum of V1 through Vs. All right. Why is that? Well, these are distinct prime factors, and we're defining Vi to be the kernels of the T fed into the prime factors, right? So the primary decomposition theorem says that you can decompose V in this way. All right. And from a theorem we did not prove yet, but we could prove without too much effort, maybe I'll do it in class for you guys, you can take the union of the basis for each one of these together and you get a basis for the whole space, all right? And the T invariance of the kernel, we have T invariance of the Vi, all right, because the Vi's are kernels. Thus, T beta I is a subset of the span of beta I. And, well, if you think about what that means in terms of the shape of the matrix, it's very revealing, right? That says if you know, for like the first one, right? Vectors taken from beta 1, they're just mapping back into beta 1, right? That means that the first, however many there are in the beta 1 space, whatever, D1, right? The first D1 columns, only going to have non-zero entries in the first D1 rows, because that's where beta 1 is in the ordering of the basis. And the same goes for beta 2 and beta s. And if you think about what that means that the matrix of T is block diagonal of the form A1, A2, .as, where these are like DI by DI blocks. In particular, you can be more precise about this. You could say AI is in fact the matrix of T restricted to Vi. That makes sense because of this condition right here. You can restrict T to the subspace VI, and it will be a mapping back into VI again, right? So you can consider the restriction of T to one of these subspaces as a linear transformation in its own right, in fact, an endomorphism of the V sub I, which then will have a dimension VI by dimension VI size matrix, in other words, DI by DI, to be precise. Now it remains to show we can choose beta I for which AI is upper triangular, as claimed. Let's see how that goes. All right. Now that takes us, so we got to define a term and prove a little lemma, then we'll eventually get back to that theorem. All right, so stick with me here. A linear transformation T is said to be, is called nilpotent. You're like, yay, another term, woohoo. Okay, anyway, nilpotent if T to the K is equal to 0 for some K. All right. In this definition, I guess we are allowing 0. 0 would be nilpotent, right? Now, here's the deal, though. Since VI is the kernel of that, the operator n sub I, which is T minus alpha I, is nilpotent when restricted to VI, right? Because n minus Ti to the EI maps to 0 if you plug in stuff from VI, right? So, in other words, Ni is nilpotent, I would say order K, because if you look at K minus 1, you might have, well, in order to say order K, I would need to know that K minus 1 was 0. I guess the order of the nilpotents doesn't matter too much to the stuff we do in here. In our way of thinking right now, it will matter if we study chains more carefully, as we probably should. Okay, anyway, getting back to track. There is something missing from this chapter of Curtis, and it's hard for me to put my finger on it exactly. I think part of it's wrapped in the fact that he does stuff in section 29 that partly should belong, in my view, in here. Anyway, I'm wrestling with something. Let me not put that on you at the moment. Let's go on here. Section so lemma 24 we're doing. Let n be nilpotent on a finite dimensional vector space W. There exists a basis W1 through Wt such that nW1 is equal to 0, nW2 is in the span of W1, nWi is in the span of W1 through Wi minus 1 for 2 less than or equal to I less than or equal to T. So in other words, you can choose a basis that's sort of stacked like this in a rather, well, let's see how you do that. All right. First of all, if n equals to 0, lemma is true. Okay. Yeah, because if n is 0, then it maps everything to 0. So like this is just sort of like vacuously like the. All right. Okay, fine. On the other hand, if n is not equal to 0, right? And there exists a k greater than or equal to 2 for which n to the k minus 1 is not equal to 0, yet n to the k is equal to 0. In other words, suppose it's nilpotent of order k. All right, if that's the case, then there exists a w, x and w, non-zero, such that n to the k minus 1 of x is not equal to 0, yet n times n to the k minus 1 is equal to 0, right? So if you let w1 equal to n to the k minus 1 of x, you can get that nw1 is equal to 0. Now that's the start of this, right? Yay, okay. And then, well, I had to think about it. And let me just get to the point here. The point's on the next page. I will say this. So I'm going to come back to this in just a second. Go on, let me show you the proof. I'll come back to my other comments in a second here. All right, so I think what I just showed you is basically the base case. All right. Now we're going to suppose inductively we found linearly independent vectors w1 through wi, for which nw1 was 0, nw2 was in the span of w1, and nwi was in the span of the first I minus 1th of the w's. Now, if w, right, is the span of w1 through wi minus 1 and wi, then we're done, because then the conditions we need would be met already up here. Otherwise, w is not equal to the span of w1 through wi, and there are two cases to consider. All right, either one, the null space of w is null. So why am I using his notation? Null space. Man, I usually say null. No, I'm an idiot. N is the transformation. I'm not. It's not null. I'm a doofus. All right, N. We're talking about N. Duh. N of W is a subset of the span. All right. Now, if that's the case, you can pick any vector that's not in the span W1 through Wi, and you can let it be the Wi plus 1. All right. Then you'll have Wi plus 1 is in the span, and you'll have linear independence of this, and from the plus minus theorem, right? If we join a vector outside the span, it gives linear independent superset for the given linear independent generating set. And then we would have met the conditions of the theorem, right? Which were, the lemma, which we're trying to show that we've got this condition, and then like n of Wi plus 1 is an element of the span of W1 through Wi, right? So if Wi plus 1 is in here, we can just add it, and then it's in the span of this with it, the Wi plus 1 tacked on there, all right? So that's one case. The other case would be that n of W is not in the span of W1 through Wi. Then, since n is nilpotent, we know that there exists a case such that n of the case equals 0, and by iteration there must exist some j for which n to the j of W is not an element of the span of these guys, but nj plus 1 is in the span, subset of the span. So we just pick the Wi plus 1 to be an element of the nj of W, right? And which is not in the span of these guys. And then we can tack that onto the set. Then we have W1 through Wi plus 1 is linearly independent, and Wi plus 1 is in the span. I think I don't want Wi plus 1. I want n of Wi plus 1, if I understand this correctly. All right. Sorry, let me put that back in frame. And this completes our induction on I. I'm not terribly satisfied in some sense with this proof. But I think we'll spend more time talking about chains, and then I'll feel better in my life when we do that. So I'm just going to leave it at that. I'm going to just go on here. Actually, I'm not going to go on. I'm going to go back. So just to say what's going on here, really, I'm going to talk about that later. I'm not going to. I'm going on. 17. All right. So now we can continue to prove the triangular form theorem because we got this lemma, which we will use. Lemma 24.2, which we just got done looking at. So the Ni is T minus alpha I. That's nilpotent on Vi. Hence, by lemma 24.2, there exists a basis, like so. Ooh, double indexing, very exciting. For which Ni of Vi1 is 0, Ni of Vi2 is in the span of Vi1, and then so forth and so on, right? And so what that looks like is T of Vi1 is alpha I Vi1. And if you look at T minus alpha I Vi2, you get this, which gives us that. And T minus alpha I Vi3 gives us K3 Vi2 plus K4 Vi1, so you start getting linear combinations possible over here. And so Vi3 is alpha Vi3 plus these guys, all right? And so forth. Eventually you get to the last one, VIK, I guess I'm saying. I think that should be, what does K go to here? I guess I just did it for the kth one. Fine, whatever. And so you get all these lovely terms. And so you get TIK is alpha VIK, VIK minus 1 plus VIKI1. Now, these are kind of messy, right? There actually is a way of simplifying this. It turns out that you can replace these linear combinations with just like one thing each time, and we'll do that when we look at these things called chains of. Look at chains of so-called. Well, let's just say when we look at chains later, this will clarify some of the stuff a little bit better. But I mean, it's not wrong, right? It's not wrong. It's just kind of messy. Anyway, long story short, we do have what we want because this is the first one, and then this just involves, like, the second column involves either the first thing in the basis and then the second thing, right? And each one of these, it has alpha in the lowest spot, and then it has the non-zero stuff above it, and that's what you need for upper triangular. And finally, to see that di is greater than or equal to ei for each I, notice that the if you have ni to the di power equal to 0, right? We have that for di equal to the dimension of vi, but we also know that v is the direct sum of v1 through vs, which implies that t minus alpha I to the I dot is equal to 0, all right? And so that means that the polynomial x minus alpha I di dot like that must be divided by the minimal polynomial, right? And so it follows then that d1 has to be greater than or equal to e1, and ds has to be greater than or equal to es all the way down the line by polynomial factoring, and there you go. That's the triangular form theorem. So just a few, let's see here if I should stop in a momento. Let me push forward here. So corollary, these are just kind of quick corollaries on the basis of the triangular form theorem. If you have T an endomorphism over finite dimensional vector space and F is algebraically closed field, mostly we mean complex numbers, okay, then the degree of the minimal polynomial is less than the dimension of V. All right, proof. Since it's algebraically closed, M is, you can write M as the product of linear factors possibly repeated. Hence, by the triangular form theorem, we have the dimension of V is d1 plus d2 plus ds, all right, where the notation is as in the theorem. And ei is less than di, so yeah. I mean, you notice that the sum of the ei's is the degree of the minimal polynomial. So these is less than those, but that's the dimension of v, so therefore the degree of the minimal polynomial is less than the dimension of v. Okay, hey, good to know. Less than or equal to the dimension of v, I should say. Definition. And you see right here is where where unfortunately I found out, I finally learned that I have been using the wrong definition of characteristic polynomial if I want to be in concert with Curtis. So sorry, guys. So endomorphism matrix with respect to some basis, then the characteristic polynomial of T is defined to be the determinant of xi minus a. All right, great. Oh noes. I usually do this. The reason I do that, guys, is so that when I'm actually calculating eigenvalues, I have less minuses to put in. Because of a 3 by 3 matrix, this involves 3 minuses, whereas that has 6 things that aren't changing, right? Like in this, on the other hand, I have to put minuses on every single thing in A, and I just find I make more mistakes when I use this for actual examples. But you know, theoretically, this is more beautiful. Fine, I get it. I get it. Just, you know, why we can't have nice things, I don't know, whatever. And then this we've proved before, but let's prove it again. Proposition, the characteristic polynomial t of x is independent of the choice beta. Also, the zeros of the characteristic polynomial t coincide with a set of distinct roots of t. There's a word missing there. Roots of the minimal polynomial of t. All right, now of t. All right, so I'm not going to, this independent, the choice of beta, we've already proved that before. We've proved that you can define the characteristic, the determinant of transformation independent of the choice of basis, and that's still true for the minimal polynomial. So I'll just focus on the other piece of the argument here. The calculation okay, I just said that. If alpha is an eigenvalue, that means there exists a vector non-zero such that TV is equal to alpha v. But that means that t minus alpha v is equal to 0 for some non-zero v. But that implies that this is not invertible, hence the determinant is 0. And that is exactly the statement that the characteristic polynomial of t evaluated at alpha is 0. Conversely, if I have the characteristic polynomial of t, if I have this as 0, that means that the determinant of t minus alpha times identity transformation is 0, but that means that there exists a v not 0 such that, and so back where we started again, we have a characteristic root, an eigenvalue of t, right? And again, the distinct, fine, I guess it's nothing. Fine. Forget the minimal polynomial here. That's not what I want either. I want to say distinct. Characteristic values. That's not what I want either. Curses. Yeah, characteristic value. That's what he's called them. So the characteristic value is the one that appears from this condition, right? Whereas the 0 of the characteristic polynomial is, well, it's a 0 of the characteristic polynomial. But these are, in fact, it's easy to get confused about why they're different, because, in fact, they are the same. That's what we just argued. So, I digress. All right, here we go. Corollary, 24.7. V being algebraically closed field. So, in other words, the triangular form theorem applies. And T, an endomorphism, M of x, the minimal polynomial, and characteristic polynomial, char T. I'm just using this. I think Curtis uses h of x for this, all right? But anyway, the characteristic polynomial of T. Then 1, the minimal polynomial divides the characteristic polynomial. 2, every 0 of the characteristic polynomial is also a 0 of the minimal polynomial. That is very useful to know. 3, the characteristic polynomial of t, when you plug in t, you get 0. This is the Cayley-Hamilton theorem. The proof is mostly by the triangular form theorem. If you look at the fact that there exists a basis beta for v for which it looks like this, well, down the diagonals you've got alpha 1 through alpha 2 and then alpha s. So if you look at xi minus t, what's that look like? It's a block diagonal matrix with like x minus alpha 1, d1 times x minus alpha 2, d2 times x minus alpha s, ds times, like that, right? And through properties of the determinant, so you got an upper triangular matrix, you just multiply the diagonals, right? And so that gives us, in fact, x minus alpha 1 to the d1, x minus alpha 2 to the d2, x minus alpha s to the ds. That's the characteristic polynomial. But what do we know? We know the minimal polynomial is x minus alpha 1 to the e1, and so forth, right? Where ej is less than dj. That was part of the triangular form theorem. So, thus, the m of x divides the characteristic polynomial of t of x, and that gives us 2. Also, think about this. If to prove Cayley-Hamilton, then it's easy. Since m of x divides the characteristic polynomial of x, that means that there's some g of x, which shows you that the characteristic polynomial is a multiple of the minimal polynomial, and that when we evaluated t, gives us g of t at m of t, but m of t is by definition 0, and so there you have it, bam. Characteristic polynomial evaluated at t is again 0. This is the Cayley-Hamilton theorem. Now, I have various points in my life. In fact, I think I've even presented this as a proof. I think in lecture one year, nobody called me on it because, well, I mean, you guys, you trust me for some reason. There are good reasons and bad reasons for trusting me. I'm afraid that the reason too often is apathy. That's not a good reason. Misguided belief that I know what I'm talking about. That's more like it. That's more what I'm looking for. No, I'm just kidding. So the characteristic polynomial is what? It's the determinant of x minus t, right? So it's tempting to think that you can just take this, right, and just plug t in, and then you get t minus t, so what's the determinant of 0? Well, it's 0, right? But that's not a valid proof, you see, because when we say plugging in t into the characteristic polynomial, we're taking the expression that's formed from the determinant of x minus t. That gives us a polynomial, and then we're plugging t into that. And there's really no reason that that should be the same as plugging t into the determinant itself. I mean, at least in principle. Now, in practice, I mean, the Cayley-Hamilton theorem is true, so you could argue, well, it works. Yeah, but that's, But my brother reads a lot, and he mentioned that he was intrigued by the fact that this book, Neil H. McCoy's Rings and Ideals, apparently builds up the definition of determinant in sufficient generality that it actually makes sense. It actually makes sense to plug in the transformation into the determinant the way he develops it in there. So it actually becomes a valid proof with considerable background being built up. It becomes a valid proof that you can plug in t there. If we trust my brother's reading of Rings and Ideals, and I do. All right. Oh, finally some examples. Yay! So I'm going to stop it and start it again here for the convenience of finding these examples.